Hello, and welcome back to our series on Vertex Operator Algebras. You brave souls have made it all the way through Lecture 27. So hopefully you've celebrated, and hopefully those technical details will pay off a bit as we prove a few claims about an extremely useful, if trivial, formal series, the delta function. But first, a quick review of some details. Let V be a vector space, and consider the space of formal sums with coefficients in V. These, you might recall, are basically maps from F to V, which we just happen to represent as a sum over formal powers of a formal variable z, and the coefficients are the image of that power in V. Also, the space of endomorphisms of V is also a vector space, and so we may also consider formal series over it. In what follows, we typically refer to such things as operators on V. One thing we often want to do with operators is to multiply them together, often at different points. But we'll also want them to collide at the same point sometimes, which we represent by taking a limit. But you might recall that this process leads to ordering ambiguities that must be dealt with. Worse than that, with so many infinite sets of things being added together, we often worry about existence of products or limits or the like. This, of course, is an abstraction of the idea of convergence, which we, in this context, refer to as summability. Given a potentially infinite family of operators, say phi, we might worry that the formal sums of them could have convergence trouble. We equate the concept of existence with summability, which means that only finitely many of these endomorphisms phi sub I acting on V are non-vanishing for all V. So, all concepts of operator algebra in this context are subject to the requirement of summability of the coefficients of the formal sums, be they the resultants of products, limits, infinite sums, or what have you. Having reviewed some highlights from last time, we now give a bit of context before delving into the properties of the delta function. First, let h hat z be that z-graded Heisenberg algebra that we studied in Chapter 1. Recall that we had a state space, or module of this algebra, which amounted to the symmetric algebra over the negatively graded subspace of that h hat z. This subspace had a vacuum vector and was itself z-graded. Indeed, it satisfied that so-called vacuum condition, which we used to prove our version of the Stone-von Neumann theorem. Virtually all the spaces we'll be considering in the future will have something akin to this vacuum condition satisfied, which means that summability is practically a given. But it's always good to know the boundaries of the sandbox inside of which you are playing. Alright, some other context that might be interesting comes from the physicist's favorite knot function, the Dirac delta function. Without diving into the full theory of distributions, we simply remind you how the Dirac delta function works in action. Suppose f is some map from R to itself, preferably some kind of integrable map, so that an integral like this makes sense. When we insert the Dirac delta function here, the integral reduces entirely to the value of the integrand at 0, or wherever the argument of the Dirac delta function vanishes. In other words, the Dirac delta function reduces the support of the integrand to a single point. We now turn our attention to a similar beast, the beast of today, the formal sum, from which we will now call the delta function. Following FLM, to demonstrate how this delta function works, we prove two separate descriptive claims. First, let V be some formal Laurent series, and let A be a non-zero element of the field F. We claim that the product V of Z times delta of AZ equals V of A inverse delta of A of Z. Proof. To prove this claim, it suffices to work with a single monomial term Vn/Zn, since the full result will follow from linearity. We first expand the product and collect like factors. Since the index of the sum runs over Z, we can shift the index as appropriate, which has the effect of adjusting the powers of A. Refactoring, we find the product we were looking for. And we're done. Next, we set up the claim about operators in the space of formal Laurent polynomials in two variables, z1 and z2. Again, let A be some non-zero member of F. For our purposes, we'll also assume that for this operator, the limit z1 goes to z2 exists. We now claim that the product of x with the delta function of a z1 z2 inverse equals two distinct but equivalent values, one for each of z1 and z2. Proof. First, we define the expansion of x in terms of its coefficients, little x, of m and n. And so we can expand the product as before and collect like factors. As before, the sums are over the integers, so we can shift one of the indices as appropriate and refactor everything to pull out the delta function. This effectively gives us one of the two representations of x, now simply as a function of z2. The main tool used in these calculations was just shifting the index for a formal sum over the integers. We leave the other result for you as an exercise, which is just a trivial rearrangement of the calculation we just did. So we're done. FLM leaves us with a remark that these delta function identities work only for integral powers of z. In particular, z to the 1/2 delta of z does not equal 1 to the 1/2 delta of z. And that's our show. Next time, we'll consider derivations of these formal sums.